Hello everyone. In this video, I am going to be explaining to you the results of my paper, which is titled Implementing the Backtracking Algorithm and the Brute Force Algorithm for Solving KenKen Puzzles. So basically, KenKen is like a Sudoku-like game where a player has to fill an n by n grid with numbers ranging from 1 to n while adhering to certain constraints. Those constraints being that each number in a row must be unique, each number in a column must be unique, and in KenKen, the grid is divided into these blocks or clusters, or what we like to call clusters. And in each cluster, there is an operation being done on that cluster and a target number for that cluster. And when we fill in numbers in the puzzle, we must make sure that each number being filled in the cluster uh, satisfies the constraint on that cluster. So for example, in this cluster here, the 60x cluster in figure 2, we've got the numbers 1, 3, 4, and 5. When we multiply all those numbers together, we get 60. So that's the meaning of the constraint on each cluster. Yeah, so basically that's an overview of what KenKen is, and maybe let's just go straight into our source code. So for our source code, we are going to be implementing our solver in CPP using backtracking and using the brute force algorithm. So here we've got a few classes. We've got the KenKen class for the main bulk of the program, and we've got the cell class, which represents a single cell in the puzzle's grid. Okay, so in a single cell, we store the value of that cell, and then and the default or empty value of a cell is 0, and then we store the target number for that cell. We store the operation being done on that cell and the coordinates that make up the cluster for that cell. And then we've got the KenKen class here, which stores the grid size of a puzzle, the grid of the puzzle, and whether or not a solution has been found for that puzzle. Okay, so before that, we actually have some txt functions that we use to store the puzzles in. And in the first line of the txt function, we store the grid size, and then on the lines following that, we store the target number for a certain cluster. We store the operation being done on that cluster, and we store the coordinates that make up a certain cluster. After that, we also have some helper functions here on the KenKen class. We've got a clear grid function to set all the values of a grid to 0. We've got a copy grid function to copy a grid. And we've also got some validator functions. This is row val returns true when all the rows, well, where all the numbers in a row are valid. This is called valid returns true when all the numbers in a column are valid or are unique. And this is cluster valid returns true when all the numbers that make up a cluster does not break that cluster's constraints. We've also got a placeable function to check whether or not if we place a certain value on a cell, will that placement make the configuration of the current state of the grid invalid. And then we've got an isSolution function to check whether or not the grid, our current grid is the actual solution to the puzzle. And then we've got our find solution backtrack function to find a solution for the KenKen puzzle using backtracking. So this k number indicates the index of the cell that we're going to set a value of, and then from this k function, it's going to be translated into an I and j integer, which basically just represents each respectively represents the row and column that we're going to set a value in. And then this backtrack function is going to iterate over all possible values for a cell, which is going to be 1 to the grid size, which is, for example, if the grid size is 5, then it's going to be going over 1 to 5, and then it checks whether or not that value is placeable on that cell. And if it is, it's going to set that value, it's going to set the value in that cell to that value, and then it checks if all values are set in a grid, it'll copy the grid to the class's grid attribute and it'll mark solution found as true. But if it's not, but if there is still a cell that has not yet been initialized with a value, then it'll fill that fill the remaining cells with values. Okay, that's basically the gist of the solution backtrack function. Mm, Next is the find solution brute force function. So this function basically it first generates all possible permutations of numbers ranging from 1 to the grid size of the grid, and it checks for all and it lists all possible permutations for a row. So for example, for a 4 by 4 grid, because there are four possible numbers 1 to 4, one row can have 24 possible combinations. And because there are four rows in a 4 by 4 grid, then there are 24 to the power of 4 possible combinations that the brute force algorithm has to check through. The brute force function will check through all those 24 to the power of 4 combinations and check this whether or not each configuration is the solution. So that's basically what the brute force function does. And then this print layout is for printing the layout. This print grid is for printing our grid. And this get solution function is used to find a solution using backtrack and using brute force, while also counting the time needed for each algorithm to perform its function. So maybe let's just go ahead and try out a function, yeah? So first we compile our code, and then we run our program. Let's say we want to do our txt file. We want to solve our 3 by 3 puzzle first. We can actually see that in our 3 by 3 puzzle here, backtracking actually takes longer than brute force. This is because on small numbers of n, in this case when n equals 3, there are actually only a few possible combinations that the brute force needs to go through. And because of that, and the fact that brute force generates solutions row by row, it it is actually faster than using backtracking. But if you try to enter a puzzle is that is of a larger size, we can actually see that the brute force takes considerably longer than using backtracking. Here, backtracking only needs 2,060 microseconds to find a solution, while brute force needs 337,680 microseconds to find their solution. So we can actually conclude that backtracking is far faster than brute force in solving KenKen puzzles, and we can actually see more of that in my paper if we read our paper here. But yeah, maybe for this video, I will leave it at that. Thank you for watching this video, and goodbye.